Yeah, comes on everyone. Let's start off. This was the last thing that we did. Great. Let's see the next one. Let's say we have a glass slab here. Factor index is mu. Distance is d. If you send a light ray at an angle of incidence I, it goes like this and it comes out. So this spot, if you look at this, so light ray was supposed to go straight, but it has gone like this. So this distance is x. X is called lateral shift. There, find angle of deviation and the lateral shift. If you send a light ray onto a slab, find the angle of deviation and the lateral shift. The lateral shift is simply the light ray, instead of going here, it is going from here. So this perpendicular distance. Let's get this thing. Others, keep your cams on. Deviation is easy. Find the lateral shift. That's an important one. So if you send a light ray, this is I, this will be R, this also will be R. So this thing comes out with I. So actually deviation is 0. So 1 into sin I is equal to mu into sin I. So the ray comes out parallel to the initial ray. Therefore, the deviation is 0. So this is x. This is what you want to find. Let this point be A. So from here, drop a perpendicular. Let this be B. Let this be C, and let this be D. If you look at this angle, this will be I minus R. So if you take triangle ABC, this distance is D. We get cos R is equal to AC by AB. AB is nothing but D secant R. If you take triangle ABD, sin I minus R is BD by AB. BD is nothing but X. AB is D secant R. Sin I minus R. There, that's your lateral shift. Numbers are given, you could substitute it, but yeah. Yeah, most of you got it. Got this? There, little geometry after that. So one thing you notice, when you send a light ray through a parallel slab, you always come out parallel. Now this, you can use it for even for multiple slabs. Let's say mu1, mu2, mu3, so on till mu1. Let's say outside the medium is mu m, this side is also the medium is mu m. So if you send a light ray at an angle theta, so once it goes inside here, we'll get R1. This will be R1. This will be R2. This will be R2. So basically, the final angle for one medium becomes the initial angle for the next medium, and so on. Finally, the light ray comes out again at an angle theta. So basically, if you apply the Snell's law here, you'll get mu medium sine theta is equal to mu1 sine I1 sine R1, which is equal to mu2 sine R2, so on till mu n sine Rn. You can clearly notice here, mu into sine I remains constant. So if they give you 100 slabs and if they ask you find the refracted angle at the 70th slab, you need not do for everything. Directly take the initial and the 70th slab. Remember, this is valid only for parallel slabs. Suppose instead of slabs, if you have a medium which is changing continuously. Let's say here the refractive index mu is 1 plus x square. Let's say here the refractive index is mu is 1 plus y square. This is your x-axis and this is your y-axis. So how do you decide the direction of normal? If the medium is changing continuously, how do you decide the direction of normal? Look at the first case, 1 plus x square, meaning for a given x, the refractive index is same. That means here the slabs are like this, isn't it? You have thin vertical slabs. For each slab, for a given x coordinate, that entire slab will have same refractive index. So here, this will be the direction of normal. If you're changing with y, then your slabs are like this. For a given y coordinate, that entire slab will have same refractive index. So here, this will be the normal. So for a medium, if someone asks you what is normal, this is how you define. So normal is in the direction in which mu changes. Suppose if mu changes radially, then mu is along the radial, right? If it is changing in 3D space. So normal is in the direction mu changes. That's one important thing. Quite a useful thing here. Now let me show you the actual question. The slabs is not the actual one. Any doubts on this? Clear? Then now see the question. So this entire first quadrant is filled with a medium mu, which is root over 1 by 4 plus 1 by y square. This is hypothetical. Such mediums don't exist, but just to make the numbers right, I gave this. Because if I put y infinity, I'm getting mu 1 by 2. Mu should be always less than 1. So just ignore that just for the sake of solving. So this is mu1, this is mu1, this is mu1. So the first quadrant is filled with medium. Now you send a light ray at the origin at an angle of 30 degrees. Now remember, we made a statement in the beginning, when a light ray enters a homogeneous medium, the uniform medium, it goes in a straight line. Here the medium mu is changing. So this light ray starts bending. Find the equation of the light ray. If you have a medium where mu changes, light ray won't go in a straight line. Let's see how you approach this. How do we approach? So here, how is the normal? Mu normal is in the direction of y. So this would be the normal here. Now for this curve here, if I draw a tangent, this is the tangent to the path of the right ray. If this angle is theta, and this angle will be 90 minus theta. Now we know from Snell's law, mu into sin I is constant. Just now we saw that thing, we proved it. Right, Purusha? So we get mu into sin I is constant. Because here you're taking, right? These are the slabs. Mu is changing with y, so these are thin slabs like this. So for given y coordinate, you have a thin slab there. So these are parallel slabs. Mu sin I is constant. So initially mu ka value is 1, you're entering at 30 degrees. So that is mu sin 30. Here the refractive index is mu and this thing is sin 90 minus theta. So mu is the refractive index at this point. Let's call the coordinates x comma y. So this will be half and mu is root over 1 by 4 plus 1 by y square is cos theta. So we get cos theta will be 2 will go there. You end up with y by root over 4 plus y square. If this is theta, y is the adjacent side. This is a root over 4 plus y square. This will be 2. So from here, we'll get tan theta is equal to 2 by y. But we know tan theta is the slope of the tangent, which is nothing but dy by dx. If you integrate this, you end up with y square by 2 is equal to 2x. Y square is equal to 4x. It's a parabola. Check. That is the main idea there. From u sin I is equal to constant, get theta. Once you got theta, tan theta is the slope. And dy by dx. And that's how you get a y and x. It's a pretty good one. Meaning I can mess up any mu function. The story is still the same. Right, Kush. Any doubts on this? You know, you have seen this kind of problems before. In physics, whenever someone asks you equation of the curve, what do you do every time? You somehow, using physics, somehow you have to get tan theta. And then you say tan theta is dy by dx and integrate this. And this is not the first time. Anyone remembers where you have done this before? You have done this 2 times. We have done this 2 times. किसको याद है? कैलकुलस नहीं है रे, वो तो एप्लीकेशन है ना. फ्लूइड्स में वेयर एग्जैक्टली 2 टाइम्स फ्लूइड में नहीं था. ग्रेविटेशन क्या बात कर रहे हो? ग्रेविटेशन में कहाँ पर है? कौन सा प्रॉब्लम था? कुछ भी मत बोल रहे. I have seen this. Fluid mein, it was one of the first problem, right? There, we got tan theta from that dmg by this thing, and then we did this thing. You know, second time where you saw? In elasticity. Remember this problem? Find the equation of the curve. We did the same thing. See, we got this slope there, eta is d by dx, and then we integrated this. We did this in elasticity. This thing again came in ray optics. So idea is this. So physics may remember this thing. Whenever they say find the equation of something, you need to get somehow tan theta using physics ka concepts. Once you got tan theta, then you do dy by dx, and then you get it. Clear with that? Keep that in mind. Generally, physics when they ask equations of the curve, that is a general tendency. That's a little about refraction on the direct light ray and everything. Then we have another application called apparent depth. You must have noticed that whenever you drop a coin or something into a bucket of water, or in a pool also, you know, it feels like the floor is much closer than it is. So we call this thing apparent depth. Again, we'll not get into any derivations or anything because all these are based on approximations. So let's say we have an object here. So what happens? This light rays will go straight, and if you take paraxial rays, means rays very close to the center here, they will deviate like this. So when you extend this backward, it feels as if the light rays are coming from O dash. So the observer here will think the object is at O dash instead of O. This distance is called H apparent. This is your H. So the formula for this, definitely copy it down. You'll need this. So H apparent is given by H by mu object. So always define first what is your object, what is the observer. So mu object, so the medium where the object is present, and mu observer. Quite a useful formula. Should definitely mark it up. Again, few precautions here. So this is valid only if the object, if line joining object and observer is perpendicular to the interface. Basically, the rays will be paraxial. Meaning if you have a situation like this, where object is here and observer is here, so this will go here, this will go here, and this is not paraxial rays. Don't use the formula here. We can't solve these things normally. The observer has to be straight on top of the object. Next thing here, all the distances are measured from the interface. So this h and h apparent are not distances between object and the observer. If the object is standing somewhere above the ground, you can't use these formulas directly. We'll see one or two examples on this. So all distances are measured from interface. There. Copied. So the thing in the red box is important. Just copy that. Refraction, it kind of looks like this. Can you see this straw here? So you kept something in a straw and you took a photograph from the side. So technically speaking, if you look at the straw here, it should have been like this, isn't it? It should have been straight like this. But see what happens. It gives you an illusion it got entirely drifted. So basically this point here became here, this point became here, and this is not paraxial. That's why this thing has gone whole to the side. Clear with this? So this you must have noticed in a pool also, right? If someone is in a pool with the head outside, it looks like the body and head are disconnected. Refraction basically. So let's see a question on this. So let's say we got a fish here. We got a bird here. The distance between the bird and the interface is h. From the interface, the fish is capital D. This refractor index is mu, outside is air1. So find apparent distance of first one, the fish as seen by the bird. Meaning fish is the object, bird is the observer. Bird as seen by the fish. So bird is an object, fish is the observer. There, let's get this. Now see, I'll help you out a little. When you do these kind of questions, right? Like I said, you can't directly use the formula. The formula is only valid for the interface. So listen carefully. The first thing is fish as seen by the bird. So the fish is the object. This guy is an observer. So you directly can't go from the fish to the observer. So this is what you do. Let's say we have an observer here. Let's call him observer 1. If you ask him, where is the fish? What will he say? Now see, if you're in the water, fish is also in the water, then there's no refraction, right? The formula is applicable only when you go from one medium to another medium. If you're just moving in the medium, nothing changes. So if you ask this person, boss, where is the fish? He will say D. Now, if you just take him out of the water, means you put your head inside the water and put your head outside the water. Now, if you ask this person, now there's a refraction. Now, you're getting it. The formula is applicable between 1 and 2. You can't apply directly between the person and the fish. What is the formula? Depth of the object, h by mu object into mu observer. So this person will say, okay, the fish is at a depth d, but inside the liquid. So d by mu object, that is mu, observer is 1. So this person will say d by mu. Now, what will this observer say? This guy will say, okay, if this guy is seeing d by mu, so he will just add up the other distance there. So the answer would be d by mu plus h. Is that making sense? So the formula, use it only at the interface. Once you're out of the medium, right, you just add the distances. Now, I have a question here. Tell me one thing. If you ask the observer 2, in which medium is the fish? What will he say? If you ask the observer 2, in which medium the fish is there, what will he say? Air or water? Let's think of like this. Imagine it's a swimming pool, very clear water. There is no reflection, nothing is there, right? When you see from the top, you don't know there is a water, right? So whatever you see, what will you think? Are there is a fish flying in the air, isn't it? Understand here, the observer is dumb. Let's say observer is just a robot. You and I know fish can't live in a water. But imagine, a 2-3-year-old kid, when he's looking at this, what will he think? You're getting the problem. We use our intelligence to figure out, boss, fish is there, matlab, there must be water. But if the water is really clear, you can't tell the difference. You will think, what? I'm in air. I can see the fish. So fish is also in air. Is that making sense? So if you ask observer 2, boss, where is the fish? He will say fish is in air. So that is one thing. Keep that in mind. The observer always think I'm in air, so everyone is in air. You're getting it? Observer feels always he is the center of the world. Right? Observer feels fish is in air. That is a catch. And that is the formula you're using the formula. The formula takes care of all that. Now, what about the other thing? The same thing. Now reverse. The fish is looking at the bird. So this is the object. Again, same story. Put a person on the water surface. He is asking where is the bird. He will say H. Now, if you bring him into the water, now there will be a refraction. Formula is applicable now. The formula is applicable only when you cross from interface to interface. So he will say, okay, if I'm outside, I would see H here. This will be mu into H. Because H by mu object is 1 into mu observer. Observer is inside the water. So the fish will say the answer is mu H plus D. All got this? Any doubts on this? Make sense?
Sir, what if there was another medium between the interface of the water?
Karate. We'll see. There you go. This is clear. Let's do one more problem, then we'll see. We'll put multiple mediums, don't worry. So how the last questions will be something like this. We have a mirror filled with a liquid. Tell me one thing, if you put a mirror inside the water and if you go inside the water and look at your image, will your image get affected? Whether the mirror is in the water or it is in air. So if you put a mirror in the water and if you go inside and look at your image will be also in which medium? Water only, right? The mirror will always think in whatever medium I am there, the image is also in the same medium. Mirrors don't get affected. Reflections in this case don't get affected. So let's say this depth is h. You kept an object here at a depth here d. Radius is r. So it's a concave mirror there. So find d if the image is on the object itself. So the final image must be on the object. Can you tell me how many phenomena are happening here? First, the light rays will hit the water here. What is this? Refraction. Then hits the mirror. Reflection. Then again they come out of the water. Refraction. Refraction, reflection, refraction. Total 3 phenomena are happening here. Let's see how do you approach this. Looks big, but it's a PYQ. Easy to solve. In less than a minute, you can solve this if you know what you're doing. Think. I'll give you a minute or two. So concave mirror filled with liquid. Let's see. Yeah. R minus H by mu, D minus H by mu. Okay. Now listen, this word, right? Whenever you hear this word, image forms on the object, that's a big clue. Huh? If the final image is in the object, that means the light rays have retraced the path. That is the catch. Quite a useful thing. Later on when we see, you will realize that if final image is on the object, this implies rays have retraced the path. So in our problem, so here the mirror thinks the object is at the center. Here the mirror thinks the after refraction, the light rays are coming from the center. That is the main catch in the question. That's it. Then you're done. So if you ask this person where is the object, he will say D. If you ask this person where is the object, he will say mu D. So if you ask the mirror where is the object, mirror will say, okay, it is mu D plus H. Now understand, mirror doesn't know who is O. Whatever light rays it will see, it will think that is O. Now because it is forming at this, it should be at the center. This should be at center. That's it. Once you're done, you're done. So mu D plus H must be equal to R. So D is equal to R minus H by mu. Got this? So if you actually look at the picture, it would look like something like this. So the light rays will go like this. They will go like this. The object is here. So there, this is your O dash. That is what is happening, and this is the center. So these letters will hit here, and they'll go back the same way they come. So they'll again retrace and they form this place. Clear? That is the thing there. Whenever you hear the word object is at the final images and the object, this is the idea there. Next thing. Now let's see what Poroja asked. So what if there are two mediums here, mu1, mu2. We will do one normally, and then I'll show you a shortcut for this. I think there's a general result you'll get, which saves you a lot of time. So observer is here. Let's say this distance is h. Object is here. This distance is t. Get this thing? Find the distance of the object as seen by the observer. So if you ask this observer, boss, where is the object? What will you say? Right. Right, Ahna. One near Poroja. Let's see. So when you do these things, right, this you should know how to do, huh? because I'm going to give a general formula, but there are chances, certain cases it doesn't work. Then you should know always how to go back to the basics and do it. Now, where are the light rays coming from? The light rays are coming from the object. So follow the light rays. So ask this person, where is the object? So 1, then ask this person, then ask this person, then ask this person. So basically there are 3 refractions. Then you'll ask this guy, and then we'll ask this guy. Making sense? So if you ask this first person, what will he say? He will say the object is at D. Because both are in the air, it will say it is D. What will 2 say? Now there is a refraction. What is the formula? Distance by mu of the object. Object is in air into mu of the medium. So 2 is in the medium mu2. So he will say it is mu2 into D. Agreed? Then 3 will say, now 3 and 2 both are in the same medium. So there is no refraction. Distance simply adds up. So 3 will say it is mu2D plus T2. Now you are going from 3 to 4. There is a refraction. The formula says, now see, this is the thing. If you ask person 4, where is the object? He will say it is in mu2. He will think light rays are coming from where? Light rays are coming from mu2. So person 4 will think light rays are coming from mu2. So object must be in mu2, right? I hope you are getting the meaning of that. Observer 4 here doesn't know who is O, who is, air and all. He will think light rays are coming from mu2. So he will think object is in mu2. So the formula becomes mu2d plus T2 by mu of the object, which is mu2, into mu of the observer. 4 is the observer into mu1. This will be D plus T2 mu1 by mu2. Lengthy, but this is how you do each step. Then if you ask person 5, he will say, okay, and just add up the distance. D plus T2 mu1 by mu2 plus T1. Now, if you ask person 6, he will say the object is in mu1 and I'm in air. So his ka formula will be 6 का formula will be D plus T2 mu1 by mu2 plus T1 by mu of the object. Person 6 will think object is in mu1. His medium is 1. This turns out to be, I forgot, there's a mu1 also here. This turns out to be D plus T1 by mu1 plus T2 by mu2. You get a pretty good result actually. So the bird will say the final answer will be H plus D plus T1 by mu1 plus T2 by mu2. You must have noticed a sequence. That means even if you have 3 slabs, I'll get something similar like this. So everyone got what we did? Lengthy, but yeah, this is how we do. So you can put on this thing. This is a more general result. And let's say we have multiple slabs. Mu1, mu2, mu1. Thickness is T1, T2, Tn. Let the distance between them be D1, D2. Let the distance be Dn. Let the observer be here, and this is H. So if you ask the observer, where is the object? Now, remember, the spaces between them are kind of useless. You can just add them up. You can just club all the slabs together. So this will be H plus D1, D2, so on till Dn plus, let's say here the medium is also mu m, mu m, mu m. So I'm just making the medium outside is not vacuum, but mu m. Then you'll have plus T1 by mu1 into mu m, T2 by mu2 into mu m, so on till Tn by mu n into mu m. So this is H plus sigma di plus mu m sigma ti by di. There, that's your apparent distance ka formula. So you can just club that, h and d1, d2, d3, the distance between the slabs is useless. You can just club them all. So it doesn't matter where you keep the slabs. The formula is valid. One thing, it is valid when the medium um is same everywhere. Imagine you mess up this medium and let's call this thing um2. Then to you're gone, na? Because if this medium is different, let's say mu dash, eventually here answer will get extra mu dash, isn't it? So that mu dash will mess up the answer. So then you'll get something little different. So here object and medium should, object and the observer must be in same medium. That's what I said. If they mess up something, you should know how to handle it. So this general method always works. And this is a faster one. Is this clear? All got this? So let me ask you this question then. Same fish and bird ka question, but let's say we'll do a little differently. Let's say we have a swimming pool, but at the bottom of the pool, there is a mirror. Refractor index is mu, depth of the pool is d. A bird is flying at a certain height, h. So the bird is looking down and is looking at its own image. So find the distance of the image. Find the distance of the bird image as seen by the bird. The bird is looking at its own image in the mirror, which is under the pool. Now, how will you do this? You can use a general method, or you can do what I taught you right now. Anything will work. So here, the bird image and the bird. So there's only one object. The bird ka image is the object. Bird is the observer. Try. I'll give you 2 minutes. It's a good one. Let's see. h mu by d 2d. Okay, let's see. I don't remember the answer actually. First, we'll go the usual way. Now, there are two parts of the problem here. First of all, you have to find the image, isn't it? Where does the image form? Will it form at h plus d? So in the first part of the problem, the mirror is the observer. Getting it? Bird is the object. First of all, you need to find where does the mirror think the object is, isn't it? The mirror will not see the bird at h plus d, it will see somewhere else. So first you need to ask the mirror, where do you see the bird? Then accordingly, I'll find the image. So mirror is the observer, bird is the object. So if you ask this guy, boss, where is the bird? He will say h. If you take him under the water, he will say how much? Mu into h. So mirror will think the bird is at a distance of mu h plus d. So accordingly, it will create an image at a distance of mu h plus d. This is your bird ka image. Is that making sense? So first mirror will think the bird is at mu h plus d. So accordingly, you'll get the image. Now your bird is there. Your bird is the observer. Your bird ka image is the object. Now understand, the bird does not know there is a mirror, there is a pool, nothing. So what will this think? The bird will think the bird ka image is inside the water. And what is this total water ka depth? This is d. And mu h plus d. Make sense? The bird will think the swimming pool ka depth is this much. The bird ka image is inside mu h plus d. So if you ask the bird, boss, what is the depth of the pool? It will think this much. Same story. So if you ask this person, boss, where is the bird ka image? He will say it is mu h plus 2d. You take him out of the water, then he will say it is mu h plus 2d by mu, which is h plus 2d by mu. So if you ask the bird, it will say it will add h to this, so it will be 2h plus 2d by mu. Got the answer? So the answer is 2h plus 2d by mu. You know how you can do this faster? So you're keeping a mirror, right? So can I just treat this thing as two slabs? The reflection is simply two slabs, isn't it? So this is d, this is d, this is mu, this is mu. So the bird is here at a distance h here. So what will happen here? So this thing feels like, so the other side, the bird image will be somewhere here. So isn't this the question? Now, what is the formula for this thing? 2h plus 2d by mu. Is that making sense? After reflecting whatever happens, it kind of looks similar, isn't it? Imagine if you just keep a bird image here, it looks kind of symmetry. You can just replace, this water, just double the distance, because this is what is happening. Refraction, reflection, refraction. Isn't that what is happening? Look at, see what is happening here. Refraction entering here, refraction, isn't it? Two refractions. The mirror simply shifted your light ray. So this boundary is useless actually. If you just flip this thing this side, doesn't this thing look similar here? Are you getting the logic? But examine if that clicks, great. If that doesn't click, your regular method is always there. Which is not difficult, yeah, little lengthy and all, but you got it. All got the question? Be careful here. First of all, you need to ask the mirror, boss, where is the bird? Then you get the image. The image is not at h plus d. Then the bird image will become the object and the bird becomes the observer. All got this? There. Next thing, so based on this apparent distance, we get a formula apparent depth. So it's all based on the same thing, apparent shift. So let's say we have a slab here, we have an object here, we have the observer here. Let this distance be d1. Let this be t, let this be d2. Let this be mu, and this be mu m, this will be mu m. So just now we derived the apparent distance ka formula. So apparent distance is d1 plus d2 plus t by mu slab into mu medium. So if you ask this person, okay, so by how much distance do you think the image is shifted? We call this thing apparent shift. This is a more easier formula to remember than the previous one. This is the actual distance minus the apparent distance. This is the shift. What is the actual distance? d1 plus d2 plus t. What is the apparent distance? d1 plus d2 plus t mu medium by mu slab. Subtract them. T into 1 minus mu medium by mu slab. That's what I said. This is a better formula to remember because it doesn't depend on d1, d2. All those are useless. So if you put a slab between an object and a mirror, the observer will think the object will shift by this much distance. Clear with this? So exactly what is happening here. So if this was the slab, so when the light rays hit a parallel slab, so initially it is going from rarer to denser, so it will go towards the normal. Then again, they'll come out parallelly. So when you retrace them, this is what will happen. So the person outside will think the light rays are coming from here. This is your O dash. This is your shift. Which is given by thickness of the slab into 1 minus mu medium by mu slab. That's it. That's what a slab does. If you put a slab between you and an object, you will think the object got closer by this much distance. Again, not a new formula. From the apparent distance, you have subtracted this. So there are a few important things here. So O dash is the shift. And the shift will be in which direction? Let me just change the color of this. So a few points here. The shift is always in the direction of incident rays. I'll tell you what it means. Second thing, the object and the observer should be in the same medium. For example, say, here the light rays are going ahead. So did you see the shift happened in the direction of incident rays? What if light rays are coming like this? The light rays are coming like this and they were supposed to meet here, but you kept a slab in the middle. Do you remember I told you this thing? What kind of things these are called? These are called virtual objects. They don't actually form. Meaning the scenario was like this: you had a lens, the light rays are coming here, and they were supposed to meet at the focus or somewhere, but you went and you brought a slab and placed in the middle. So these light rays, instead of meeting here, will get diverged a bit. So these light rays will go somewhat like this, and they'll convert somewhere here, O dash. So this is the shift. Is this making sense? So when this formula is written, T into 1 minus mu m by mu slab, the shift will happen in the direction of the incident rays. Whichever direction the light rays are going, the image will form on that side. Right? And the best thing about this, you can use this for multiple slabs. Let's say if you have multiple slabs, you can, for all of them, you can use at the same time. So this is T1, mu1, T2, mu2, Tn, mu n. And let's say we have an object here. So it doesn't matter what the distance between them, the total shift will be sigma summation Ti 1 minus mu medium by mu I. There. This is independent of distance between the slabs. It doesn't matter. You can keep the slabs together, keep where this is a shift. That this is the more generalized formula. We proved for one slab, you can make it for n slabs. Any doubt so far? Go take a break, come back by 9:40. Any doubt so far? Sure, come back by 9:40. Find the final position of the image. Two problems. So you have a concave mirror, in front of it you kept a slab. So again, how many phenomena are happening here? Slab, mirror, slab. 3. So light rays will first go through the slab, then hit the mirror, then again go through the slab. So then the image which forms, that is your final image. So remember that whenever they say image, they are expecting you to find all refractions and all reflections. Let's get this. Right, Ahna. Get the next one. Yeah, first one is easy. Get the next one. How do you do this thing? Look at the first one. So when x is 21 centimeters. So forget about the mirror. This is what I keep saying. When you talk about the slab, don't talk about the mirror. And when you talk about the mirror, don't talk about the slab, one at a time. Others, keep your cams on. So this is your object. The shift is how much? T into 1 minus mu medium by mu slab. So this is 2 centimeters. Mu is also 2. So this is 2 into 1 minus half is 1 centimeter. So every time you go through the slab, it will shift the image by 1 centimeter. Now in the first problem, so if you ask the mirror, where is the object? It will not say O, it will think O dash is the object. And this distance becomes 20 centimeters, which actually becomes the center. That means the light rays will go here, and will again come back the same way. Question is still not over. So now if you ask the slab, boss, where is the final image? So the slab will think, okay, light rays are coming from here and they were trying to meet at the center, which is the O dash. But again, whenever you go through the slab, the image gets shifted by how much again? By 1 centimeter. Is that making sense? So the light rays have retraced the path, so they'll go back again 1 centimeter backwards. So the final image is 21 centimeters from mirror. Is that making sense? So first the slab will shift by 1 centimeter. Great. Slab ho gaya, just throw it outside. The mirror will think the object is at the center. It will try to form the image at the center. Mirror is done. Throw the mirror outside. Now put the slab again. Now slab will think the image is supposed to form at 20, but it will push 1 centimeter ahead. The final image is at 21. Is this clear? One at a time. When you talk about the slab, don't talk about the mirror. Vice versa. Can you get the second one? I'll give you a minute. The 31 centimeters. Yeah, most of you got it. But others, try for a minute. Same question. If it is 31 centimeters, what you do? The story is still the same. Yeah. So in B part, again, same story. If you ask the mirror, where is the object? So this is O, but mirror will think O dash is the object. Again, remember the shift is 1 centimeter. So the mirror thinks the object is at 30 centimeters. Mirror doesn't know who is O dash. So this is what is actually happening. These light rays are going like this. And after refraction and everything, they start, it feels like as if you're coming from here. Something like this. So apply the formula for mirror, 1 by V plus 1 by U. U is minus 30 centimeters. Radius is 20 centimeters. R is negative. So focal length is 1 by minus 10. So V is minus 15 centimeters. That means this mirror is trying to put the image at 15 centimeters. So this would be the image. Let's call it I dash. 15 centimeters from the mirror. Then you know what will happen. This will again get shifted forward by final image here. Let's call it I final. 1 centimeter more. 16 centimeters from mirror. All got this? That's what a slab does. Any doubts on this? So be careful. You have to use the slab twice. So that is the first question you always ask. How many phenomena are happening here? Let's say we got a slab whose refractive index is changing 1 plus x by t. This is x is equal to 0. Let's call it L. Better, x is equal to L. So we got a slab of length L, 1 plus x by L. Object is here, observer is here. Find the shift. You got a slab with variable refractive index, which is changing from 1 to 2. It doesn't matter, right? See, there's nothing called converging inside the slab. It is an illusion, isn't it? Tell me one thing. Does the mirror know there is a slab? Does the final observer know there is a slab? If you're standing here, do you know there is a slab?
No.
You will never know there is a slab. You will. So what you're saying is, if the light rays come and meet here, let it meet. No, it doesn't matter. Remember this formula? The shift is always in the direction of light rays. So whether they meet inside, outside, in front, the shift will be always 1 centimeter ahead.
But shift was depending on the thickness of the slab, right?
हाँ.
slab के बीच में converge कर गया तो it's not like the covering the whole thickness of the slab.
Okay. And then दूसरा slab क्या कर रहा है? What is the slab in front of it doing then?
Okay.
Forward. If you cut it here, चलो तेरा logical है तो ये है ना, चलो ये slab ये था, then ये slab क्या कर रहा था? It won't do anything. After light rays come here, this will do nothing.
अच्छा, okay sir.
वो भी shift करेगा. It will become T1 plus T2 into 1 minus mu1 by mu2. So T1 plus T2 is T. It doesn't matter.
Okay sir.
तेरा लॉजिक वही है ना, सेंटर में फॉर्म है, ठीक है ना, कट कर ले दो स्लैब में, एक शिफ्ट और एक शिफ्ट वापस शिफ्ट होगा. It won't make a difference. Puroja, you took average and did it क्या? अरे आंसर रॉन्ग है. इंटीग्रेट करना है. आई होप ऑल इंटीग्रेटेड. So if you're not integrated, you won't get the answer. Let's get this. There's only one formula there. 1 minus mu medium by mu slab. That is the only formula. Nere Puroja, you're moving up. Check properly. नहीं आदित्य, राइट रहा ना. See, so at a distance x, take a thin slab dx. The shift is so small, so d shift will be, the formula is what, t into 1 minus 1 by mu. So t is the thickness of the slab. So dx is the thickness of this thin slab. Shift will be 1 minus mu outside is 1 by mu slab, which is 1 plus x by 2. Just integrate this directly. The shift will be integral dx minus integral dx by 1 plus x by L. 0 to L, 0 to L. This will be L minus L ln 1 plus x by L. Limits will go from 0 to L. We'll get ln 1 minus ln 2. Yeah, that's your answer. If shift is negative means what? So for example, let's after calculating you got a negative number. What does it mean? It is not going in the direction of light rays. It is going opposite to the direction of incident rays. So the science will take care of it in case the image is actually forming backward. This is easy. See where it went wrong, integration where you messed up. Any doubts on this? Next one. This is a good one, right? This could be a good mains level question. So we have a container here. We have an object at rest. We also have an observer at rest. Now what you did, you started pouring water into the container. So when you're continuously pouring water or liquid or whatever, so this surface is going up with V. So the surface is going up with V, the thickness of the slab is changing. Find the velocity of the object as seen by the observer. It's a good one. Let's see how many of you will fall into the trap. It doesn't matter, Repurvaj. The distance between the object observer and the liquid surface won't matter. And it does matter in a way, but I don't need to give any values. How do we do this? Mhm. Okay, that looks right, Ravish. Mu is given. I'm sorry. Mu of the liquid is mu, outside is 1. Hmm. So if you can somehow find the apparent, Hana, you fell into the trap. Roja, you got it. Vihan, you got it. So listen, the catch in this problem is this. You just need to find the apparent shift first, apparent distance. So let this distance be y and let this distance be x. Now, what most people don't realize is when the liquid level is rising up, y and x both will change, isn't it? X and y are distances from the interface. If the interface is moving, both and x and y are getting messed up. That's the first thing you need to realize. So if you ask this person, where is the object? So he will say, this is at a distance of x by mu plus y. So if you differentiate this, you will get apparent speed. One by mu dx by dt, dy by dt. Now you have to be little careful here. When, if you see, because of v, what is happening to x? X is increasing, so it is v by mu. When the surface is going up, what is happening to y? Y is decreasing, so minus v. Is that clear, everyone? Since y is decreasing, dy by dt is minus v since y decreases. This comes out to negative. That means the object is not coming towards him, it is going away from him. Is that clear, everyone? You can make this better. Same question if it is like this. Let's say observer is coming down with V1, surface is going with V2, object is going up with V3. Now what will be the answer? If all are moving? So the formula is still same. So H apparent is x by mu plus y. So when you take the speed here, 1 by mu dx by dt. Now ask yourself. So x is the distance between the upper surface and the lower surface. Is v2 increasing x or decreasing x? v2 is increasing x. What is v3 doing? v3 is decreasing x, so v2 minus v3. dy by dt, y is the distance between this. So what is v1 doing? v1 is decreasing y, v2 is also decreasing y, minus v1 minus v2. Is that making sense? So if the velocity is decreasing that particular quantity, then it is a minus of that. Both decrease y. v2 increases y, increases x. Is this making sense? So be careful with the signs. That's the simplest way to see and figure it out. Is this velocity increasing this y coordinate or x coordinate? Increasing, plus, decreasing, minus, done discussion. Keep it simple. Any doubts on this? Then that is about your apparent depth and slabs and all that stuff. The next thing, all clear with this? Optical fibers. Again, this is just a theory there. These are, if you see our current technology and everything, right? Even today, the class we are able to take is all because of this only. If you go back to 1980s, even early 1990s, right? If anyone has a telephone in their house, that means they must be pretty damn rich. So getting a telephone connection, right? You need to be really you need to be rich or you need to be really politically connected. So telephone connection, the reason used to be see, I'll tell you one simple thing. Before these optical cables, right? If you want to send a signal, we used to use copper wires. Now let's say if you have 10 houses and you want to connect them with the telephone line, we used to have telephone exchanges. I don't know if you have seen these old movies. The hero or some person calls and says, operator, please connect me to so and so person, and then they connect them. So think of a grid like this. Let's say we have 5 people, A, B, C, D, E. We have 5 people, 1, 2, 3, 4, 5. So what the operator does, they have plugs here. If the person C wants to talk to person 4, then we close this plug. Then 4 and C can talk. You get in the connections how they give? So if the person 5 wants to talk to B, then close this switch. 5 and B can talk. So literally you have a grid there. These people used to have a full board there with a lot of holes there, and you take the plug, connect here, and the telephone is connected. So you used to have a job called a telephone operator, right? And this person's job is that only, and it is not 1 or 2 people. Literally, it used to be full of exchanges. And generally, right, during war ka time mein, it was a pretty popular job among girls because men used to go into war and die. So there used to be someone has to be there for communication, right? So they used to take over this entire telecommunication and everything. Now, the problem with this thing, can you see here? You need a wire for every house. Now, just imagine your housing society. If you have 100 apartments, everyone wants a telephone. 100 copper wires will come out of the society. Your entire street will get, filled up with wires and everything. It's a mess. If B wants to talk to C, then you have one more private line here. So you close this and you close this. So you'll keep one extra line here. So you can do that. There's a lot of stuff. Even today, right, you still go through an operator, but that operator is a computer program. So when you dial the number, it takes care of everything and happens instantaneously. There's no delay. So the biggest problem we had was through a copper wire, you can send only one signal at a time. That was the biggest headache. It was slow, and if you use a copper wire, every 2 to 3 kilometers, the signal used to die down. So you have to have a booster. Becomes expensive. But optical fibers, right, will solve a lot of problems. If you ever seen an optical fiber, right? If you go to your router and if you open that thing, you will find something like this. The router ka cable. All your internet cables will have things like this inside. You can see how dense it is. It's not one single optical cable. It has multiple layers inside it. So this is how it looks. So we have inside that optical fiber, it's like a kind of a glass kind of thing, plastic kind of thing actually. And then we have a copper thing, and then we have a sheet, and then overall cladding and everything for protection. You must have even seen toys of these optical fibers. Seen this kind of toys in any fair or something? You put a bulb there and you put optical fiber, the light simply goes through each of them. That's actually the light going them. They're not colored. Never seen this? If you ever been to any fair or beach, you will find stuff like this. And just like, we have roads and, airlines or railway lines and everything, we also have underwater sea cables. This is the underwater sea cable ka world map. Literally, you can see these lines. These are underwater sea cables, meaning underwater sea cable kind of looks like this. There, this is an underwater sea cable. So every day, right, there are ships all over the world which are laying this, optical fibers under the ocean. You can see how dense the network here is between Europe and US. So whenever you want to make a phone call to someone in US, so from Mumbai, right, this phone call goes to Dubai. From Dubai ka servers, it goes to Europe servers. Europe se it will go to US. So whenever you're talking on phone, no, we are not using satellites. We are actually using optical cables. So if I make a phone call to you, why all that right now when I'm talking to you, what's happening? I'm talking to you, the signal is going, wireless from my this to my device. Device it is going to my router. Router it is going through an optical cable and it is coming all to your houses. So all this communication we are doing right now is happening through optical cables. So what makes these things so special? Meaning, just imagine here. Can you see this one tiny city here? Something, and that must be some Maldives or Mauritius or something. So let's say if a ship goes there and accidentally cuts off this cable here, internet goes off. There, there have been cases like that. In Europe, right? If you see now, there are certain networks here. There was an old lady, she was farming, she found a wire in her farm, she got pissed off, she cut it off. And that was the whole internet connection to one of the full, I think some European full country lost the internet connection because of that. They do have backups, but sometimes it just gets overloaded. Look at this thing also here. See one small city here. So yeah. So we have satellite phones. Satellite phones is a different term completely. You send a signal to the satellite in space and then you get it back. In India, it is banned. You catch a satellite phone and walk, they'll catch you. You will get arrested. So some foreigners, right, they accidentally bring a satellite phone into India without knowing, they get arrested in the airport. If you remember that Mumbai terror attacks also, right, the terrorists actually use satellite phones. So satellite phones are difficult to track. So people can do, illegal stuff and you don't know what they're doing. So you can't track them. So normally military people use them in Himalayas and all when wars are going on, right? So for communication, they use them in the middle of the hills. You can't have optical fiber during war. So we're in the mountains and all. So what makes this so special? So if you look at the construction of this, let's say this is mu1, this is mu2. So the core is denser. This is a radar medium. Idea is pretty simple. It works on principle of TIR. So you send a light ray at an angle I. This becomes R. It hits the mirror here. This angle becomes 90 minus R. So you just have to make sure if the 90 minus R becomes greater than critical angle, what will happen? It bounces off. This also will be 90 minus R. Then this angle also will be 90 minus R. Means again it will bounce off. You're getting it. This light ray will never stop. this ray will just keep on bouncing inside the thing, and it is going with the speed of light. So when I'm talking to you, even though you guys are so far and all, it takes fraction of a second for the sound to reach you. There is a delay. So when I'm talking to you and when you're receiving, the delay might be something like 0.001 second. You don't notice it. We call it a lag, right? Sometimes the net is bad. You can see that it is lagging. So the advantage of this thing, you know what? In a copper wire, if I can't send two signals at the same time, they'll interfere. But you remember in light, there's a statement, if two light rays pass through each other, what happens? Nothing happens. They just pass through each other. You can send 1 lakh light signals through a single optical cable and they don't interfere with each other. So for your society, if you see, right, you must have noticed it. That entire one building, you get only 1 or 2 wires for internet connection. And that one internet wire, they put a router and they spread it to 10 houses. Never noticed that? Every house doesn't get 1 wire. Your entire society gets 1 wire, and that is split into some 10, and that each one is split into another 10. The bandwidth just keeps on, splitting. And that 1 wire can carry almost 1 terabyte per second information. You can reach that kind of speeds. So the kind of optical network we have in India, right? You can reach speeds of almost something like 1 terabyte per second, not 1 gigabyte. So you have that kind of bandwidth, but then again, when I think about that, I still, think about my IIT ka days. In IIT, we used to have an internet speed of 556 kbps. 56 kilobytes per second. So if you want to download a movie of 700 MB, right? It used to take aram se 3-4 hours. Now तो कुछ भी नहीं है. 700 MB movie मतलब you will laugh also. You want a 4 GB some HD print. So we used to be happy watching a movie of 160 MB, a highly compressed, pixelated movie. We are okay at least to see a movie. Anyway, so it used to be like that. So here, if you use Snell's law here, this would be sin I. Mu1 sin r. So we get sin r is equal to 1 by mu1 sin I. Sin theta critical is mu2 by mu1. There's just one small thing here. There's nothing much to solve in this. So 90 minus r must be greater than theta critical, right? So then the light ray bounces inside. That is the whole point of it, transmitting a signal. This was the CET question. Optical fiber works on which principle? Total internal reflection. Sin 90 minus r is greater than sin theta critical. This will become cos. This will be 1 minus sin square. R is greater than sin theta critical. Sin r is nothing but 1 minus sin square I by mu1 square is greater than. You simplify this, you end up with I is equal to sin inverse root over mu1 square by mu2 square. There. That's your condition for the light ray to bounce inside. So if you get this angle to be like, say, like 37 degrees, when I can send a light ray at 36, 35.9, 35.85, 35.8, I can send like, every half of degree, I can send one light ray. And all these things will just keep bouncing inside and I can collect them at different angles. So when you're actually looking at your telephone wires right now, right, these optical fibers, they have like something like they'll allot 10% for phone calls and everything. Almost 40-30% is gone for data. And they still have some redundancy. They still have around 40-50% more capacity still empty. Yeah, if you bend the fiber too much, it will escape. So every 4 or 5 kilometers, they have a signal booster. So you have to amplify the signal every 4-5 kilometers. So the more you bend it, yeah, the signal does escape. It does lose a lot of energy. That is all there. Clear with us? That's a bit about optical fiber and refraction on a plane surface. The next thing is a refraction on a curved surface. Again, like I said, as long as you know the formula and the sign convention, everything looks similar. In CET, this itself will be a question. They'll just ask the formula and one simple things there, formula and numbers. So mu1, mu2, radius r. So here the interface is not a flat surface, but it is a curved. Let's say this is your image. You can note down the formula here. Mu2 by V minus mu1 by U is mu2 minus mu1 by R. The magnification का formula is minus mu1 V by mu2 U. What is mu1? Mu1 is the medium of incident rays. So the medium from which the light rays come and fall on the interface is the mu1. Remember that way. Mu2 is the medium where the light rays will enter. Medium of the refracted rays. So when they come and fall on a interface, the medium they're coming from is mu1, the medium they're entering is mu2. Same stuff like we did in mirrors. U, V, R must be taken with sign convention, and the object must be on the principal axis and valid for paraxial rays. So same assumptions. If the object is not on the principal axis, you know the process, whatever we did in mirrors, still valid. The only thing that changes is the formula. All the techniques you learned are same. You can note down the formulas there. All clear? Let's say mu is 2 here, 3 by 2, 20 centimeters. Object is here. Forty centimeter. Find the position of the image. Here object is at a height. Find the position of the image. There, just direct formula substitutions. 20, 60 minus 20. Let me help you with this. See, first thing, define your mu1, mu2 properly. What is mu1? Lighters are going from left to right. Mu1 is 2. What is mu2? 3 by 2. What is u? Minus 40. What is radius? Plus 20. Check. If you got this, you're done. It is just a matter of putting in the formula. So the formula mu2 by v. So 3 by 2v minus mu1 by u, 2 by minus 40, mu2 minus mu1, that is minus half 20. So this is 3 by 2v minus 1 by 40. It will go that side. So minus 2 by 40, that is minus 3 by 40. 3 goes off. V is equal to minus 20 centimeters. Minus 20 indicates the lighters have bounced like this. And when you extend them backward, the image is forming here 20 centimeters backward. It's a virtual image. Are you getting the meaning of this? Same story here. Mu1, 3 by 2. Mu2, 4 by 3. Numbers are bad. U is minus 20. R is also minus 20. Substitute in the formula. 4 by 3 V minus 3 by 2 U. Mu2 minus mu1. How much is that? 9 minus 8. 1 by 6 minus 20. Minus 1 by 20 plus 3 by 40. Multiply 3, 120. 9 minus 1, 8 by 120. That will be 8 by 120 is how much? 1 by 15. That will be 3, 5. V is 20 centimeters. Am I right? I got V is 20. Plus I got. So it is actually converging on the other side. What about the magnification? Magnification is minus mu1 V by mu2 U. Mu1 is 3 by 2, 4 by 3, V is 20, U is minus 20. 20 goes off, 9 by 8. That means you have an image on the other side at 20 centimeters, and plus means it is on the same side, right? So image is 9 by 8 to 9 by 4 centimeters. Got this? Four by 3 minus 3 by 2 is minus 1 by 6. So सही बोल रहे हो, that's minus 1 by 6. This will become plus then. This will become minus. I did 2 mistakes. Am I still right? No, no. This will be then minus 1 by 15. Still right? This will be minus 1 by 15, right? Then this will be minus 20, na? So the image is actually virtual. I think this is minus. So you'll get a minus. So actually get an inverted image. Interestingly, at the same place. But this time the height is 9 by 4 centimeters. Right? You got the calculations, check it out. But got this thing? Lengthy. Like I said, na, these problems where there's nothing to think. You know the formula, just put there and solve and solve and solve. Any doubts on this? Next one. This, if you got it, then I'll understand you know the formula. We have a glass sphere. Mu is equal to 2. Now this glass sphere is silvered. Means you made it a concave mirror here. Outside is 1. Radius is r. Object is here. This distance is r. Find the final image. How many phenomena are happening here? Refraction, reflection, refraction. The refraction on curved surface, then use mirror, then use refraction on curved surface. Again, remember, when you're using refraction, don't talk about mirror. When you're doing mirror, don't talk about refraction, one at a time. So the image of one system becomes the object for the next system and so on. So refraction on curved surface, then mirror, then refraction on curved surface. And also be careful that distance are always measured from respect to poles. Get this, you got 2 to 3 minutes. This would be a good question. The first part only you'll get confused. Think. नहीं, that's not the answer रे. कुछ उसके बाद refraction नहीं होगा क्या? Let's see. Did you guys get the first part? You got 1 by v 0. Means what? V is not 0. V is infinity. Light rays will become parallel. Hope you realized it. So let's say the first refraction. Let's do each part. So object is here. 2, this is 1. Mu1 is 1. Mu2 is 2. U is minus R. Radius is plus R. So 2 by V minus 1 by minus R is equal to 2 minus 1 by R. We get 2 by V is 0. This implies V has become infinity. Meaning the light rays are meeting at infinity, meaning the light rays have become parallel. People do get confused. They don't understand. They think it is 0. It is not. So after hitting this, light rays have become parallel. That actually makes your life easy. This is your first part. So for the second part, now you have a mirror. If the parallel light rays go and hit a mirror, you know what happens. Now the light rays are inside. The parallel rays will meet at the focus. Let's call this thing I2. And this distance is R by 2. This is your reflection. Or let's call it just mirror. The third part. Now be careful here. Now the light rays are coming from here, I2, like this. That's what this interface thinks. This is your second refraction. Hope you're getting how you're doing this. Mu1, now see again, what is mu1 now? Mu1 is 2. Mu1 is the medium for where the light rays are hitting the interface. The light rays are coming from inside and hitting the interface. Mu1 is 1, the medium where the light rays are going into. The light rays are going into vacuum. So mu1 is 1 and the light rays are coming from 2. U is minus 3r by 2. Now be careful. The distances are measured from the respective pole. So this is the pole. This distance is 3r by 2. The center is also on the left hand side. So radius is minus r. Substitute in the formula. This is mu2 by v. So 1 by v minus 1 mu2 by mu1 by u. Minus 3r by 2 mu2 minus mu1 minus 1 by minus r. 1 by r. We get v is equal to minus 3r. Got this? So what is the meaning of minus 3r? So the minus 3r is the light rays have become like this. If you trace them backward, they meet somewhere here. This is I3. And this distance is 3r from here. So it's a virtual image which is forming at a distance of r on the other side, meaning the image is here, final image is here, I3. Who is seeing that? If you have an observer standing here, he will think it is there. You're getting it? That is the meaning of it, the final image. All clear with this? So refraction, curved surface ka formula, then mirror ka formula, then again refraction ka formula. You have to use it multiple times. Minus 3, and be careful with the signs. And the distances are supposed to be measured from the respective poles. All clear with this? Yeah, so that's a bit about it. Next class, when we catch up, we'll continue with this. We'll see more variations of this refraction on curved surface. Again, whatever you did in mirrors, everything will come. Object is moving, all that stuff. We'll play around with that. It's a small part. Once this is done, we will go ahead with lenses. There's also something on prisms that will keep it for the end. The next class will be quite important. We'll be starting off with introduction of lenses also. That will be a little more important. But again, ideas are same. What you did in mirrors, everything you will do the same thing. But lenses, there are 1 or 2 little more points also. Mostly, I think next week we will wrap up the chapter. And then, yeah. Okay, with that, we'll wrap up for that day. And do remember, there's a test online on current electricity, 60 questions. So don't miss out the test. It will be quite helpful. So make sure to give. If you don't give anyway, I'm going to catch you in the class. So anyways. Okay, with that, we'll wrap up for that day. So anyone has any doubts in the class notes, anything else, stay back, or else you're free to leave. I'll see you on Friday, same time again. So take care. Stay safe.